the end of our death march together. Let me make sure that we can see me there. All right. Hello. Welcome to AP Physics C. We're going to talk about rotational energy today. I'm Mr. John Frensley from Prosper High School in Prosper, Texas, about 3 miles north of Dallas. And I've not been doing a good job of saying whether the stuff I'm talking about is good or aligns also with P1. So those of you who are teaching AP Physics 1 out there, yesterday's video on rotational forces and torques and today's on rotational energy are pretty friendly to P1. There's not a lot of calculus involved there. For AP Physics C, it would be just a lot more mathy, than in P1, but we go over some good concepts here too, because they might show up on this year's exam in either course, all right. So we're going to start with a warm up here. And so remember, the emphasis today is thinking about phenomena in terms of rotational energy, but some force torque concepts might show up again as well. So just be on the lookout for those. Okay, so what have I got here? I've got this contraption. For those of you who are teachers, you might recognize this from the 2001 AP Physics C mechanics exam, question 3, I believe. So we've got a heavy block M. I hope you can see it right here. And it's attached to this thing, which I call a whirligig. I actually built some of these. I work with my students in P1. So we wrap the string around this post of radius R. And then we've got this rod up here, length of 2L, and we have a block M and a block lowercase m. And I'm not going to read the whole paragraph to you. It's just suffice it to say the 2 M's are the only thing that really have mass, not the rod, not the post, okay? And then, of course, the hanging mass has some mass, right? So the system is released and allowed to fall a distance D. Are you looking at this? I'm circling it. That's how far the big block is allowed to fall. So now we've got a student who's trying to derive an equation for the velocity of the block at the end of its falling distance D. They come up with this equation right here, which I think you can see it's kind of covered up by the zoom watermark. So that's an L squared down there at the bottom behind the Z of the zoom watermark right there. So here's what you're going to have to do. You've got to look at this equation. There are 6 letters in this equation. And you've got to ask yourself, which of those letters are out of place? Which ones are in the wrong side of their fraction bar to make this not plausible? So you get 3 minutes to examine all 6 variables. Which of these variables are on the wrong side of the fraction bar, making this not a plausible equation? On your mark, get set, 3 minutes. So in a nutshell, everything in this fraction down here is bad. That's all bad. So if you addressed all 4 of those variables, you hit it on the head. So G is in the right place. It's in the numerator. More gravity would make the block go faster because there'd be like more energy. More potential energy becomes more kinetic energy, right? And D would mean that more potential energy became more kinetic energy if you let it fall farther. So the farther you fall, or the more gravity, the faster you go. So G and D are in the right place, but all 4 of these letters in this little fraction down here are in the wrong place. So look at where the big M is placed. If the big M were bigger, this whole fraction would be bigger, which would make the denominator bigger, which would make the V smaller. Did you follow that logic? If the big M were bigger, then the equation says the whole denominator is bigger, which makes the velocity smaller. But that doesn't make sense. If you hung a bigger mass, it would have more potential energy or more force to pull on the rotating contraption, and it would spin faster and the block would fall faster. Okay, what about R? Well, look at what the equation says. More R would make the denominator, this big denominator, bigger, which would make the velocity smaller. But that actually doesn't make sense, because if the post were a bigger radius, then the string would apply more torque, and more torque would mean more rotation, which means the string would be let out faster and the big block would be able to fall faster. So more mass or more radius should result in faster fall speed, but the way they're placed, they would make this big denominator bigger and they would make the velocity smaller. Now, I'm just going to put these next 2 paragraphs up here. You can read them, but I'm going to summarize. This thing I'm circling right now with my mouse, this little ml squared, that's actually the rotational inertia of this whole jazz up at the top, right? Okay, so this whole swinging arm thing up at the top has a rotational inertia, 2ml squared. Now let's think for a moment. What does the equation say? The equation says if there's more rotational inertia at the arms, then this smaller fraction will be a smaller number, making this bigger denominator a smaller denominator, right? So think about that again. If the rotational inertia is bigger, this fraction is smaller. That makes the whole denominator smaller, and a smaller denominator means a bigger velocity. Well, that doesn't make sense. You shouldn't get a faster velocity for the arms having more rotational inertia. You should get a slower velocity. More inertia is harder to speed up. So this one was tricky because it was a compound fraction. The fraction in the denominator was bad. So these 2 things on the top should have been in the denominator of the fraction's fraction, and then these things on the bottom should have been in the numerator of the fraction's fraction. Isn't that tricky? So again, on AP Physics 1, they're not going to do something as tricky as a compound fraction. Physics C, I got no guarantees, because there's going to be some complicated math on there that you have to write about. You're going to have to write about complicated math. Yikes, isn't that terrible? Okay, so we want you to be able to describe energy transformations that take place involving a rotating object, apply conservation of energy to calculate unknown quantities, and then be able to just make predictions using conservation of energy involving rotation, right? Okay, so here's what you need to know. So when atoms move, the atoms have kinetic energy, and all the kinetic energies of all the atoms add up, right? So when you have a translational motion, you have translational kinetic energy, 1/2 mv squared. Now, the easiest way to talk about translational kinetic energy is to think in terms of, you guessed it, the object's center of mass. So the m is the mass of the object, and the v is the center of mass velocity of the object, right? Now, on the other hand, if you have a rotational motion, then your atoms are still moving, but they're moving in circles around some axis. And so we call that, we say that that's a rotational kinetic energy, right? So all the little 1/2 mv squareds of all the atoms going in circles add up to what's called the rotational kinetic energy of the object. So if translational kinetic energy is 1/2 m, how difficult it is to speed up or slow down your translation, v, how fast your translation is, squared, then rotational kinetic energy would be 1/2 I, how difficult it is to speed up or slow down your rotation, times omega, how fast you rotate, squared. So in both cases, it's 1/2 times how difficult it is to increase or decrease this motion, m for translation, I for rotation, times the rate at which this motion is taking place, v for translation, omega for rotation, squared. All right, so there you go. And it's all on the formula chart anyway. You should really have, if you don't have a copy of the formula chart and you can't print one, please go online and write out the formula. I know that's going to be annoying. It'll take you 10 minutes, but write out the formula chart for this year's exam. All right. So can you have both energies? Can you have both types of energy at the same time, translation and rotation? Of course you can. It is possible to have both types of kinetic energy at the same time. So you have translational kinetic energy if the center mass is translating somewhere, going left, right, up, down. You have rotational kinetic energy if you have some kind of rotation around an axis, around the center mass. So the total kinetic energy of an object is the sum of its translational rotational kinetic energy. And watch out, on the AP exam, if they just say what is the kinetic energy of this object, and the object has both types, kinetic translation, rotation, then just saying kinetic energy implies that you have to talk about the sum of the two. If they talk about one specific one, translational, rotational, they're only talking about that one. But if they just say kinetic energy with no other adjective in front, translational, rotational, you are implicitly looking at the sum of them. Okay, so 1/2 mv squared if your center mass is moving, 1/2 I omega squared if your atoms are making circles around an axis like rotation, right? Okay, so a mass M is attached to a string and it's wrapped around a pulley wheel. Okay, so I want you to imagine that. It's like an Atwood machine, but he's missing his left half, right? So we've got the mass and it's going around a pulley wheel, right? And we're going to let go of the mass. And as the mass falls, the pulley wheel is going to rotate, right? Okay, so what if the pulley wheel had so little mass that we basically can ignore its rotational inertia? What if the pulley had low rotational inertia, not zero, not negligible, but low? What if the pulley had high rotational inertia? So think to yourself, you got three of these. You got super light wheel that we can basically ignore its mass, low rotational inertia, high rotational inertia, all equal blocks. We just let them go. Who would win that race, right? Which block would win the race at the bottom, right? So how would rotational inertia affect the falling mass? Well, I have a little animation here. So what you'll see here is you'll see the yellow block is not attached to anything. That's going to be our control. Okay, that's going to be like the free fall block, right? And then you'll see the blue block is attached to the blue wheel. But the blue wheel is so close to massless that we can treat it as it has no mass, no rotational inertia. So you'll notice if the pulley wheel is super light, then the blue block falls just as well as the yellow block because it's as if the blue wheel is not even there. It doesn't contribute any to the inertia. But now look at the green and the red. The green and the red have those masses attached to them like I showed you in my animations yesterday. Green has the gray masses close to the center, low rotational inertia, and red has the masses on the outside, high rotational inertia. So what I hope you're seeing here is I hope you're seeing when the animation starts, which right now you have 4 bar charts, one for each of these situations, and all the energy is gravitational potential energy. That's the blue bar. And it's all 6 squares. Watch now, all 6 squares of the blue potential energy bar are lit up. For the yellow and the blue, all the gravitational energy becomes translational energy. But wait a minute, Friendsley, isn't the blue wheel rotating? Sure is, but it's such little mass that it doesn't count for any inertia. So you would do 1/2 I omega squared for that blue, but I is so close to 0 that you just get close to 0. So why does the yellow and blue block win? Because all their potential energy turns into translational kinetic energy, which is V, speed, right? The green, some of its some of its potential energy for green, some turns into rotation. That's the yellow bar with a KR. So some of the UG turns into KR for the green wheel. So not all the energy gets to go to translation. Not all the energy gets to go to speed of the green block falling. Then for the red, having more rotational inertia, even more energy goes to rotating the wheel. So the more rotational inertia, the more energy goes to rotating the wheel, the less goes to translating the block down. So the block goes slower speed, the more rotational inertia it's attached to. So hopefully these kind of animations with the bar charts show you how the energy is divided up based on the rotational inertia of the wheel. Okay, so what if I wanted to solve for the speed, right? So with what speed does the block strike the ground? So let's say that the block's mass is m, okay, little m, and the pulley wheel is capital M and it has a radius of r and it has a shape constant of k. So I'm going to start with potential energy of the little block. So that's mgy, right? So you see the y here in the diagram and the little m, right? Okay, all delicious. Now, what is that going to turn into? That's going to turn into 2 energies. It's going to turn into the rotational kinetic energy of the wheel because we got to rotate the wheel to let the string out, and the translational kinetic energy of the block. And this V is what I want to solve for. I want to solve for that V. How fast does the block reach the ground? So the conservation of energy equation would look like this. We start with potential energy, mgy, and we're going to divvy that potential energy out, sum to the translation of the block falling and sum to the rotation of the wheel. So that's the 1/2 mv squared of the block and the 1/2 I omega squared of the wheel. Okay, all good. So now I'm going to plug in. My goal is to solve for V, but watch out. V is related to the omega of the wheel. The faster the block falls, the bigger, faster the omega of the wheel. So we got to link those up somehow, right? So I'm going to plug in two things. One, rotational inertia is K, which depends on the shape, mr squared of the wheel. Okay, right? Remember, K is like 1/2 for a disk and 2/5 for a square, or for a sphere, I mean, or whatever. And then V equals omega R. This is a good one to remember, that the translational V of the block and the rotational omega of the wheel is related by V equals omega R. R is the radius of the wheel. As long as there's no slipping happening. If there's any kind of slipping happening with the rope, or when we roll down an incline and there's slipping, don't go with V equals omega R, because they aren't the same because of the slipping. So I'm going to plug all that in. So I got my mgy, my 1/2 mv squared, my 1/2, here's my rotational inertia, my V over R. Now, if you write this out, you'll notice that this R squared in the numerator and that R squared in the denominator will actually cancel out. In fact, I just distributed the square here on this next line. So R squared in the numerator, R squared in the denominator cancel out. And so I'm also going to factor out the V. There's a V in both these terms and there's a 1/2. So it looks like this. It's going to look like mgy equals 1/2. And then the little m and the shape and the big M are going to factor out V squared. So then I'm just going to multiply by 2, divide by that m plus km, and take the square root. So I'm going to get something that looks like this. All right, so there you go. So I want to look at the features of this result. I want to see what actually helps the block hit the ground faster. So what's going to help the block hit the ground faster? Well, let's look. The higher the shape constant, that means more atoms are on the outside of the wheel. The higher the shape constant, or the higher the pulley's mass, the less speed I reach the ground with, because more energy is going to be diverted toward rotational kinetic energy of the wheel, and less is going to go to the translation of the block down the incline. That makes sense, okay? Now, if we have a very, very, very high hanging block, if the hanging block is so huge compared to the mass of the pulley wheel, then if this M is so big, then we just get V equals radical 2gy, which is the same result we would get if we just let the block free fall, right? And then, so there you go. We would get V equals radical 2gy, which is what you got for the yellow and the blue block in that animation that were basically just in free fall, right? The farther you fall, the faster you'll fall. Okay, that makes perfect sense. That's why I don't jump out the window right now, okay? The more gravity you have, the faster you fall, which is why I don't jump out of windows on Jupiter, right? Okay, so it makes perfect sense. Here's a way of explaining it with forces. So what you'll notice here is I added a pink weight force to each of the blocks. They all have the same weight. However, the more rotational inertia, the more tension is needed to get the wheel to go, because tension is what's torquing the wheel into motion. So the red wheel takes a lot of tension to get it to go. The green wheel, some tension, but the blue wheel is so light, and then this one's just in free fall, the yellow, that they have basically no tension acting on them. The rope is slack. Well, the more tension opposes your motion, the harder it is to accelerate down. So this red case has a lot of tension opposing the weight vector. So that means you don't get a lot of acceleration, takes you a long time to fall. Green, a little bit of tension opposes the weight force. So you get some acceleration, right? So you fall, and then the other two have no forces opposing weight. So we fall at 9.8 meters seconds squared. All right, so see, we can explain what goes on in these simple situations, either through the lens of forces and torques or through the lens of energy, right? Okay, let's talk about rolling objects. If an object is rolling, it has both translational kinetic energy because its center mass is going down the incline or up the incline. And then it also has rotational kinetic energy because the atoms are making circles around the center. So there's two kind of ways you can roll. You can roll with slipping and you can roll without slipping. And you're going to find out that rolling without slipping is easier than rolling with slipping. I'm just going to tell you that right now, okay? So rolling without slipping is really easy. So there's no skidding. There's no against the surface like that as the object rolls. equals. And so when that's the case, the rotation and the translation have kind of a synchronous that goes on. Like if you're translating fast, you're also rotating fast and vice versa, right? And so then you get to use V equals omega R if you're rolling without slipping. And the same goes on those ropes around the wheel. If the rope doesn't slip, then you can use V equals omega R to synchronize the V translation and the omega rotation, right? If you're slipping, then either V or omega R are bigger. One is bigger than the other. For example, if your V is bigger than your omega R, then you're skidding to a stop, right? Like watch how my hand is barely rotating, but my V is fast. So this is V is bigger than omega R. On the other hand, peeling out would be that your omega R is way faster than your V. So that would be slipping, right? If you can say V equals omega R because you're not slipping, you can also say A equals alpha R like we did in the last lesson with torques, right? So that's allowed. This is a big one. The friction that acts when you're not slipping is static friction. Even though you're moving, if you're not slipping, it's static friction. So if your teacher taught you that static friction acts when an object doesn't move, shame on them, because static friction acts when an object does not slip or slide. See, there's a difference there. You can move and not slip or slide. When you roll without slipping, you have a static friction, which means you cannot say friction equals mu normal. Static friction doesn't do his best. He does less than his best. Okay, he's like some of my students, unfortunately, right? So, and this is a third one. Static friction cannot dissipate energy. You cannot lose energy to friction, which is great because then I can use conservation of energy. So rolling without slipping, V equals omega R and A equals alpha R, go for it. Friction equals mu normal, don't even touch it. Conservation of energy, go nuts. It's great. All right, so I like rolling without slipping. Just don't say friction equals mu normal. Okay, now if you roll and you slip, then you have a peeling out or a skidding that I just demonstrated my little window here, okay? And if the wheel is peeling out, then the V is less than omega R. We talked about that. If they're skidding, then the V is greater than omega R, so you can't make those things equal to each other, but you can use friction equals mu normal because if you slip, you have kinetic friction, and kinetic friction always does this best. So kinetic friction always is max strength, right? But you will lose energy to dissipated form, sound, heat, that kind of thing. So if you roll and slip, I don't go for energy there because that's a nightmare. I would try to do forces and torques instead. Okay, so here's a little bit of guided practice. So hopefully you've had this conversation with your teacher before, but if not, we're having it here. And if you have, we're having it here anyway. I want you to imagine three objects are at the top of the three identical inclines. You got a block of ice, no friction. You've got a disc and a hoop, right? Now the disc and the hoop are going to roll without slipping. The ice is obviously going to slip without friction because it's ice, all right? The wheel and the hoop have this, the disc and the hoop have the same radius. All three have the same mass. So everyone's the same mass. Disc and the hoop, same radius. They don't slip. Ice definitely slips without friction. You're going to rank the objects based on the following. Which one reaches the bottom of the incline first? And explain your ranking in terms of energy principles. Okay, so this is just one ranking. Rank them based on who wins the race. All right, you get 2 minutes to tell me who wins the race, who gets the silver, and who gets the bronze. Go. All good. So hopefully you already knew it was going to be the ice that wins, then the disc, then the hoop. Now, once again, I'm going to point out that in this animation, you see the spokes right here. So there's green spokes, and then there's some little red spokes on that hoop there. And to show that they're not slipping, each spoke intersects the incline at a white dot. So every time it goes over a white dot, the light green or light red spoke touches the dot in order to show you that these, in fact, are not slipping. Okay, so here's my ranking. Ice wins, then disc, then hoop. Here's my explanation. They all start with the same gravitational potential energy, same height, same mass. Same mass, same height. And you can see here with the pie charts, and you can see with the bar charts that they all start with the same blue gravitational potential energy. Now, no energy is dissipated because for the ice, there's no friction at all. And for the disc and hoop, there's a static friction because we're not rolling. Only kinetic friction can dissipate energy. Now, the block of ice is going to change all of its gravitational potential energy into translational kinetic energy. So all the blue potential energy turns into green translational energy. On the other hand, the other two are going to have to pay some of their potential energy into rotation. The disk has less rotational inertia. Because the disk has less rotational inertia, it pays less of its energy into rotation. Whereas the hoop has more rotational inertia, so it pays more of its energy into rotational. So that means that the disk has the second most translational kinetic energy, goes the second fastest, takes the second most time, whereas the hoop has the least translational kinetic energy, slowest speed, it takes the most time. Okay, did I say all that? More energy goes into rotation for an object with rotational inertia. The greater the share of energy going to translation, the faster the object goes. That's the ice. So the ice wins. It's all translational kinetic energy for him. And the hoop loses because it's least translational kinetic energy for the hoop. All right, isn't that glorious? Yay. Okay. So suppose the three objects, so let's show this mathematically. Let's say all the objects have the same mass m, they start the same height y, okay? To find the speed of the ice block, that's really easy. We're just going to take potential energy and make it translational kinetic energy. So then you're just going to get v equals radical 2gy. Okay, great. Okay, now, all right, that should be easy. I hope you don't have to go back and see that. But what if I'm going to do the disc or the hoop, right? So we're going to start with mgy potential energy, but we're going to end with both translation and rotation. So here's mgy potential energy equals translational kinetic plus rotational kinetic energy. Okay, now what am I going to say? I'm going to plug in v equals omega r. All right, so omega is now going to turn into v over r, and the rotational inertia is going to be shape mr squared. Disc and hoop had the same m. Disc and hoop had the same r. Disc and hoop have different k's. The shape of a disc is 1/2. The shape of a hoop is 1 full one, right? Okay. Once again, you'll observe that I can distribute the square, and then this r and that r cancel top to bottom. Not only do the r's cancel top to bottom, but the m is in every term. So the m cancels term to term, and the r squareds cancel top to bottom. So then I just get something that looks like this. Let me get rid of my m's. There we go. I just get gy equals half of v squared plus half the shape constant v squared. Look at how that's simplified, right? Now let's double everybody. Let's add like terms with the v squared. That means factor out the v squared, and then let's solve. So I'm going to factor out the 1/2 and the v squared. I'm going to solve for v by doubling, dividing by 1 plus k, and then taking the square root. So what do we learn from this? What we learn from this is that the speed at the bottom depends only on the gravity, the height of the ramp, that makes sense. And it only depends on the shape, not even the mass or radius of the object. So what that means is that if you have a sphere, k is 2/5, and you have a hoop, k is 1, the sphere will always beat the ring. If I take my wedding ring and put it on an incline and put the moon on the same incline, the moon will win the race, even though it's a much greater mass and radius, assuming the incline could support that, right? So what do we see? We see that the speed of the object depends only on the height of the incline and gravity, of course, but it also depends on the shape constant, not on the mass or radius of the object. So The shape constant of something that only slides is 0. The ice does not rotate. The shape constant of the disc is 1/2, and the shape constant of the hoop is 1. So as you try a higher and higher shape constant, the velocity at the bottom, and therefore the velocity will be less and less for a higher shape constant. The time it takes will take more and more time. In fact, the shape constant is actually what determines this ratio right here. So the shape constant of 1/2 for a disc determines the 2 out of 3 and 1 out of 3 ratio of the translational and rotational kinetic energy. The shape constant of 1 determines the 1 out of 2 and 1 out of 2 nature. And I'm not going to go into that. You can prove that on your own. But it's the shape that matters for who wins the race, not even the mass or the radius. Now, I'm going to remind you that we can also talk about this in terms of forces. So all three of them have the same mg force. They all have the same weight force. So they have the same mg sine theta down the plane. But the more rotational inertia you have, the more friction it takes to torque you around. So you'll see that the green disc and the red hoop have a friction that torque them around to get them to rotate. But the ring has more rotational inertia, so it takes more friction to torque it into its motion, which means there's more friction opposing the translation down the hill. So more friction opposing the translation down the hill for the ring, the harder it is to go. So does the ring lose the race because he has more friction holding it back in order to torque him into motion? Or does the ring lose because he has to pay more of his energy to rotation, less to translation? The answer, yes. Okay, so that's all there is there. Now, let's take our three objects again: ice, disc, hoop. They're going to roll side by side on a flat bit. Then they're going to approach an incline. Who's going to go up higher? So I want you to rank the objects based on which goes higher up the incline and tell me why in terms of the energies involved. Okay, on your mark, get set, 2 minutes. Music. What do you know about that? Okay, all good. And the end. Okay, so here's an animation of what's going on. So they all start with the same translational kinetic energy. That's the green bar. But watch out. If they all start with the same translational kinetic energy, then that means that the disc has some rotational kinetic energy and the hoop has even more. See, it's the opposite now, right? So why is that? Well, the rotational kinetic energy, 1/2 I omega squared, they all have the same omega for having the same speed, but hoop has a lot of I, disc has a little I, ice has no I. So if you'll watch at the beginning of the animation, all three green translational kinetic energy bars are 4 bar units. Ice has no rotation. The disc has 2 rotation kinetic energies, and the hoop has 4 rotational kinetic energies. So the hoop having more total kinetic energy can climb up the hill farther to a higher potential energy. So the hoop has a greater I, has a greater rotational kinetic energy, therefore it has a greater total kinetic energy. So the hoop has more total kinetic energy than the disc, more total kinetic energy than the ice. So then all that kinetic energy becomes potential energy. So the ice has very little kinetic energy to give to GPE. The disc has more kinetic energy to give to MGY, and the hoop has a lot of kinetic energy to give to MGY. So the ice goes the least distance, and the hoop goes the most distance. All right, so that was my energy reasoning. Here's my forces reasoning, okay? Let's just do this really quickly. How high can the ice block go? Well, how high can the ice block go? We're just going to take his translational energy and set it equal to potential energy. So you're just going to get this thing that's just height equals his speed squared over 2g. Okay, all good. But how high up then could the ring go or the disc go? Of course, the faster the block, the highest it goes. If you're on a bigger gravity planet, you won't go as high. Okay, that all makes sense, right? But let's talk about what if we're doing the ring or the disc. So for the ring or the disc, watch what we have. We have their translational and their rotational energy become mgy. Their translational and their rotational energy become mgy. So I'm going to plug in my v, my omega is v over r, my I is kmr squared. I'm going to cancel all the r's again, top to bottom. I'm going to cancel the m in every term. Okay, all good. So we can see that the r squared is going to cancel out. It's just the same as we've been doing before. Okay, and then the m is in every term. So now let me solve for the y. So I'm going to divide by g, and I'm going to factor out the half and the v squared. And you're like, wait a minute, Frensley, isn't this what you just did, only you're solving for a different variable? Yes, this is what I just did. I'm just solving for a different variable. It's the same thing again. All right, so what do we got here? We've got height is 1 plus k times v squared over 2g. So the bigger the shape constant, the higher up the incline you're going to go. The ice has no shape constant, so he just gets v squared over 2g. The disc has half, so it'd be 1.5 v squared over 2g. And the hoop would be 1 plus a shape constant of 1, 2 v squared over 2g, right? So the higher your shape constant, the farther up the incline you can go. It all depends on the shape. It doesn't even depend on mass and radius. Those things cancel out. Okay, once again, we can talk about this in terms of forces. Do you remember yesterday when we said that friction always points uphill when an object rolls on an incline without slipping? Well, the ring has more friction uphill. The hoop has more friction uphill because he needs more torque to slow down his huge rotational inertia. And then the ice has no friction helping him at all. So the ring goes farther up the hill because he has more friction helping him up the hill. But the friction isn't thinking, I'm helping the ring. The friction's thinking, I'm trying to slow down the ring's rotation, and this is hard to do. And then the disc has a little bit of friction helping him up the hill. The ice has no friction helping him up the hill. So you can see it through an energy lens or a forces lens. You choose which one you prefer. Hopefully on the AP exam, they won't ask you to talk about both. They have done that in Physics 1 in the past, specifically on this topic right here. Okay, 2 more practice problems and then we're going to go. So suppose we have 3 identical discs, okay? We're going to name them red, green, and blue. Blue is on a perfectly frictionless incline. Green is on a low friction incline, so he's going to slip as he goes down. Red is on an incline with lots of friction, so red does not slip. So you're going to do 2 rankings. You're going to rank red, green, and blue based on the speed reaching the bottom and the total kinetic energy they have upon reaching the bottom, okay? So this is rolling and slipping. The discs are identical, but they're on different inclines. On your mark, get set, rank. Now, I know I'm going to go a little bit over time. I have one more 3-minute little practice problem for you, but after that, we have a big announcement. So don't just tune out because it's 45 after the hour, right? Okay, here's my animation. Please note that the disc that's on the frictionless surface doesn't even rotate. It has no friction to make it rotate, so it doesn't even rotate. Whereas the disc that's on the surface and slips, and look very carefully, that wheel is slipping. You can see that the spokes do not intersect each of the white dots like it does for the red, right? The red is not slipping. So the green has a little bit of friction, and the red has a lot of friction because static friction is stronger than kinetic friction. So notice I'm arguing in terms of forces whenever I deal with rolling and slipping. Okay, so I say blue wins, then green, then red is the least speed at the end. Here's the animation. Blue has no friction, then green has some weak kinetic friction, and red has some strong static friction. And the weak kinetic friction is having a lot of trouble getting that green up into rotating, whereas the strong static friction has no problem getting red to rotate, right? So there's more friction on the red on the green, no friction on the blue. So the blue is going to win the race with no opposing force, and red is going to lose the race with a lot of opposing friction force. Now let's talk about the energy. We'll look carefully at these energy bar charts. So we see that all of the gravitational energy goes into translation for the blue, no friction. And all the gravitational energy goes into translation and rotation for the red, because static friction can't take away energy. But look at the green, and you see that red energy dissipated. I call it ED. My students love that. There's some red energy dissipated because kinetic friction dissipates energy. There, yeah, you can hear it there with the sound. So blue and red end with the most tied kinetic energy. Blue has no friction, so there's no energy loss to other forms. Red rolls without slipping. Static friction can't dissipate energy, but green slips, kinetic friction totally dissipates energy. So watch that in the energy bar charts. Do you like that? That's a really good concept question I would totally ask on a P1 exam, and this year a C exam too, right? Because this year is a whole writing exam, right? Okay, so it's going to be the same rules again, only this time we're going to roll horizontally. Blue is going to encounter a perfectly frictionless incline. Green, low friction, so it slips. Red, high friction, so that it doesn't slip up the incline, right? So they're all side by side on their respective tracks, rolling without slipping. But then blue, frictionless, green, low friction, slip. Red, high friction, slip. Rank them based on how high they make it up the hill. Rank them based on their total kinetic energy at the moment that each one reaches its highest point. Okay, so on your mark, get set, take a stab at this. almost done here. Okay, so let's look at an animation and see what happens. So what you'll notice is that the disc that slips, it doesn't stop rotating because it's got no friction to make it stop rotating, right? But no friction helping it up the hill. So it's not going to go that far. Whereas friction is trying to get the green to slow down. Oh, he's going to slow down. Oh, he doesn't quite slow down to 0, right? So friction's trying to get the green to slow down. He's got a little bit of friction helping him up the hill. Friction's definitely helping the red up the hill, all right, because that's a static friction. It's very strong friction, right? So we got a lot of static friction helping the red up the hill, not so much with the green. The blue, none at all. So the red goes the highest, then the green, then the blue. Then we're going to think about it using force concepts. Friction points up the hill. The better the friction up the hill, the farther up the hill you go. Okay, I'll let you pause this if you're on the non-live view, and you can read it for yourself. Okay, now let's look at this in terms of energy, right? So it turns out that blue has the most this is not correct right here. Please ignore this. It's that I must have done a copy and paste mistake and not corrected. Blue has the most kinetic energy at its highest point because it doesn't stop rotating. It does stop translating. Green has the second most kinetic energy when it stops, because when it stops, it has no translation, but it still has a little bit of a rotation. And red has no kinetic energy at its highest point. I'm really sorry. That's a copy and paste mistake. So it should have been blue has the most kinetic energy because he's still rotating. Green has a little bit of rotation still, and red has no rotation, and they all have no translational kinetic energy at their highest point. So I apologize about that. That was wrong. So let me just get off that screen. Okay, so here's a summary, just really quick. You have translational kinetic energy if your center mass moves. You have rotational kinetic energy if your atoms make circles around the axis. It's possible to have both types of kinetic energy. A rolling object experiences static friction if it doesn't slip, kinetic friction if it does. You only dissipate energy if you slip, which is kinetic friction, right? If there's no friction at all, or you roll without slipping, you can use conservation of energy because you don't lose anything to friction. Rolling system can usually be analyzed through the lens of forces or torques, or through the lens of energy, right? Okay. Oh, well, I guess the debrief and summary slide made it after the summary slide. Well, I'm batting 1,000 today. Okay, so tomorrow, Angela's going to go over angular momentum with you, and she's going to have a special guest who's going to talk to you about the tech side of taking your AP exam, right? What is it going to actually feel like when the questions appear on the screen and there's a timer, and how you're going to actually respond. So be there for that. And then Monday, Angela is going to hold a mock AP exam, and she's going to use resources provided by the College Board. And on Tuesday, she's going to go over it like a scoring rubric type thing. And then Wednesday, I'm going to proctor a mock exam through YouTube. And here's the deal. I think I'm going to have permission for this. I haven't quite gotten it yet. I'm going to write my own AP Physics C questions that I think will model what looks like on this year's exam. So this is questions that no one's seen before, not my own students, not any of your teachers, not anybody. They're not on my Facebook page, nothing. You've never seen before. So if you want to see those questions and be part of the live mock exam that I'm providing, then tune in Wednesday, 11 a.m. Eastern, 8 Pacific, I think I'm doing that right. Anyway, and then Thursday we'll go over it, and then Friday we're going to have like some kind of like a meeting. It's going to be me and Angela. This is Friday next week, where we're going to sort of pool together and give you the best tips that we can to get you ready for your AP exam on Monday, May 11th. All right. So I hope to see you all there, and thanks for joining us on these videos. I hope they've been useful to you. See you next week.